With that being said, again, I would like to welcome everybody to today's Qatar Transportation webcast. In a moment, I will hand the presentation over today to Xiaoping or Shaw Lee. Let me tell you a little bit about Shaw, and then I will hand the remainder of the time over to him. So Dr. Xiaoping Lee is currently an associate professor and a Susan A. Bracken faculty fellow in the Department of Civil and Environmental Engineering at the University of South Florida. His major research interest includes traffic modeling, control, and advanced network systems with applications in connected autonomous vehicles, shared mobility, and electric vehicles. He is a recipient of the National Science Foundation Career Award. He has published 47 journal articles. He has served as a member of the Transportation Network Modeling Committee and the Traffic Flow Theory and Characteristics of the Transportation Research Board. He has served as a department associate editor for the Institute of Industrial and Systems Engineer Transactions and on the editorial board for the Transportation Research Part C. Okay, Shaw, take it away.
Sure.
I'm here.
Hi, everyone. Good afternoon. And it's my great pleasure to present my work here at Qatar webinar. So today I'm gonna and thanks Daphne for that great introduction. And today I'm going to talk about the control of connected autonomous vehicles in mixed traffic environment. I'm not just going to talk about theoretical models, but I will also talk about field experiments and some practical insights. So connected vehicles, as we all know, are just like communications, vehicles with communication furnished in vehicles, and the vehicles can talk to each other, infrastructure units, pedestrians, and anything around. Autonomous vehicles, and there is a video, I guess, it basically means that human drivers are actually going to be replaced by robot drivers. And so this way, human don't have to drive, and we can just be riders, and the computers can take over all the driving tasks. So next page. With these innovations, actually, we have a new dimension of transportation management, as opposed to traditional infrastructure-based management styles. Now we can actually look into the vehicles because we have the opportunities to control the vehicle trajectory level detail. And for example, we can control the vehicle trajectories to let it be smoother. And this way, the traditional transportation management problem can be potentially transformed from accommodating the human driving in the past to designing vehicle trajectories of connected autonomous vehicles in the future. So this opens up a number of opportunities for CAV trajectory design research. And there have been excellent work done in this area by our peer scholars and practitioners. But yet there are still quite some challenging problems pending. Most existing studies focus on individual vehicles in controlled environments, whereas streams of vehicles on a road segment, including mixed traffic with human drivers and complex environment, may still need to be investigated. And in the past, I talked to friends from industry, those companies that are working on autonomous vehicles, and they are primarily focused on very computationally expensive algorithms using fancy GPUs, expensive sensors, and computing devices. And but there is going to be a need to sort of improve the algorithm efficiency and make it real-time applicable and scalable to a corridor or even network scale. And most of the studies were focus on numerical and general data-driven approaches, and the analytical insights and traffic flow domain methods and physics are still missing, and they may potentially largely help improve these models and algorithms controlling connected autonomous vehicles. And most studies as of now at universities are simulation, and there are only limited studies on field experiments. In particular, there is almost no study on CAV operations and control in mixed traffic environment. So to address these challenges, our approach on CAV trajectory design takes this general framework. So we're going to start from the theoretical aspects to really look into the structure and fundamentals physics of the systems. That's going to help us to develop really fast algorithms and for either exactly solving some special problems or populating some faster heuristics to get to reasonably well algorithms in very low computational with very low computational complexity, so that can be easily implemented to terminal vehicles with a relatively low cost. And eventually we're going to validate and demonstrate these developments with field experiments. So today I'm going to talk about some of these studies more on the high-level thoughts rather than detailed techniques according to this framework. So let's just give you an example about a core problem we're looking at actually. So these are just like a controlling of the autonomous vehicles in the stream of traffic. So for example, this is a time-space diagram. X is the time and Y is space. It could be a road segment, could be a turning section. Basically it shows the longitudinal course of a number of vehicles that are indexed from I through 1 through I, and each of them is going to have some kind of speed and acceleration movements. If you want to spread them out over the space, they're going to form time-space vehicle trajectories, and we can control the shapes of these vehicle trajectories subject to physical, mechanical, and communication and computing limits. So and the physical limits included the speed limits, like normally when a vehicle drives on the roadway, it doesn't back up, and there is a speed limit that sort of bounds the maximum speed, and accelerations is bounded by driving comfort as well as the vehicle's mechanical limits. And also there are, because we're considering a stream of vehicles rather than individual vehicles, so we need to consider the safeties between vehicles. In particular, the falling headway, sort of like the safety between two consecutive vehicles following one another. And we want them to separate far enough, for example, with a certain time and space headway to make sure that the vehicle's operations are safe. And just for those who understand traffic flow theory, and this treatment is quite similar to the fundamental diagram, one type of fundamental diagram called triangular fundamental diagram proposed by Newell and D'Agenzo. And with this, so how do we really control these vehicle trajectories? What kind of objectives we want to achieve by controlling the vehicle trajectories? Really what are we going to do with the flexibility of an autonomous vehicle control? I think from a system perspective, if you're a transportation operator, what you want to do is mostly come from the three aspects. For example, mobility. You want to make sure that vehicles can, or users can get to the destinations from the origins in the minimum travel time. And driving comfort is, or it's like the acceleration, deceleration is not too dramatic and stops are not too many. Fuel consumption or emissions, it's like you don't want vehicles to have, you want vehicles to be fuel efficiency, and you want them to emit, have as minimal emissions as possible. And also for safety, you want the system to be as safe as possible, and there are a number of safety surrogate measures that can be used to quantify the safety. So basically, we can quantify all these different objects as formulated here. You don't need to understand the detail of the mass, but the point is, these measures, if they are higher, some for mobility measures, we want to make it higher. For driving comfort, fuel consumption, safety measures, we want to make it lower. And as if we combine all of them together, we're gonna sort of like minimize a system of objective that, for example, that includes the components of maximize mobility, minimizing fuel consumption, and safety risks. And if you integrate this combined optimization objective with a number of the constraints we mentioned earlier about vehicle kinematics, about safety and other things, we actually can come up with general CAV control framework. And I can say most of the CAV design trajectory control framework are following this paradigm. So we're going to optimize the vehicle trajectories to achieve a certain objective, and either for a subset of vehicles or for the entire traffic stream. And from a transportation engineering perspective, we're also very interested in the impact to an entire traffic stream or even a network. So this is going to result in a very complex nonlinear programming problem, for those who know, with differential constraints, but whatever it is, it's very complex to solve. So we really need to understand the essence of the problem to really get a hang on it. So we want to look into the structure of the problem, the analytical insights, to simplify this problem. For example, just to give you some examples, we sort of shift the coordinates, to put these trajectories close enough to compare them and on all these different measures, including safety. And with that, we also do some feasibility analysis for vehicle trajectories. For example, if you know a vehicle starts from this time point at this location speed, and it wants to get to the final location or range as illustrated by this bold segment at time t, you can calculate the possible range for vehicle trajectories as this kind of like, I call it a quadratic prism. So you can quantify the range of its possible activities. And that's only for one individual vehicle, regardless of other vehicles' impacts. But if you put it into context of multiple vehicles, you're sort of analyzing this kind of feasible prisms between different vehicles, and you're going to identify a band or a sort of like a modified prism to host this vehicle's trajectory, feasible trajectory. And you can do that for all these vehicles, and that will give you sort of intuitive understanding about the possible ranges in time and space for these vehicles to appear, and that's gonna exclude lots of time-space points where it is infeasible or unsafe for vehicles to get there. And with this kind of analysis, we can actually find to solve optimal trajectory control for certain special objectives, just like minimizing the travel time alone, this kind of thing. And further, we can actually, for even more general optimization problems, we can use this kind of analysis to much simplify the numerical solution approach to make the exact solution procedure a lot simpler, because for example, we reduce the so-called state space of decision variables in this optimization problem for those who know it. I'll be quick on this. And besides on the exact algorithms, like what's the best we can do, we can also develop some really practical fast heuristic. For example, with this kind of analysis, after we know the feasible regions, we can find some smooth trajectories within these feasible regions, and with some really simple, for example, piecewise polynomial trajectories to construct them as smooth trajectories. In this particular instance, you can see we can design these vehicle trajectories to be smooth and pass these signalized intersections right at the start of the green time without even stopping. So this is gonna have lots of benefits on all the measures, all the objectives, including safety, energy, and mobility. So, and we also did some analysis comparing the exact algorithm methods and fast heuristic, and we see for some reasonable conditions, these, even if we use a very fast heuristic that may not do the problem the best, but it's gonna solve the problem somewhere close to the best, and it's a really acceptable solution. And so this is actually gives lots of practical it provides very efficient tools to solve practical vehicle control problems, and that needs the efficiency because practically speaking, all the CAV controls are dealing with millisecond level control, and you have to let your algorithm respond fast and in real time. And with this approach, we can get really so-called near optimal efficient solution approach that can solve the problem in almost no time, and the solution control is already very close to the optimum, if not exactly at the optimality. So these are just like theoretical part. Now I'm gonna get into something that is fun about field experiments. These theoretical analysis and algorithm developments provide real-time methods for design smooth trajectories for real-world CAV control. Yet it's not convincing to just present the algorithms and theories, and doesn't bring much sort of real-world impact or technology transfer implications without the field experiments with real-world vehicles. So fortunately, we collaborated with partner institutes, and they have a state-of-art facility like test track. So and also some cutting-edge connected autonomous vehicles, and they have the infrastructure, but they don't have the control algorithms. We provide our control algorithms, so we're able to really integrate our tests to perform a set of interesting experiments. Let's see how to turn off this. Yeah. So with that, I'm gonna introduce a set of tests we have done. So the first test is actually, if you can see this vehicle, there is no driver, so it's just to show that this is autonomous vehicle. But actually, in other runs, we do put a driver there to switch this vehicle from an autonomous mode to the human-driven mode. So basically, this example is to test how human drivers react to autonomous vehicle driving in front. So we tested 10 drivers, and we put the first vehicle, and we put the first vehicle as the at either autonomous vehicle mode or human-driven mode, and we have it drive on either constant speed or dynamic lead vehicle speed, and then we compare the different responses from this human driver to this autonomous vehicle in either human-driven or autonomous mode, and we looked into the relationships between the time headway and space headway, such as the space headway and time headway on this. This can be easily interpreted with this time-space diagram, where the first curve is actually the lead vehicle's trajectory, and the second curve is the following human-driven vehicle's trajectory. And the first vehicle is either on the human-driven mode or autonomous mode, and we compared actually the distance gap and the time headway for these two different modes, and we find some drivers are indifferent to. Some drivers are actually, for example, if you look at n equals 1, this is a representative driver that is sort of tech phobic. It reserves a longer spacing and a longer distance gap and a longer time headway when following autonomous vehicles. So this driver doesn't trust the technology. Whereas the n equals to the middle two, the middle column shows that this driver is indifferent to following either autonomous vehicle or a human-driven vehicle. Whereas n equals 8, the third column, we see actually it maintains a closer headway or distance gap when following the autonomous vehicle as opposed to the human-driven vehicle. So this last driver is sort of a tech pro and trusts the new technology, and we sort of categorize all the drivers into these three categories. And we also tested we try to have the first vehicle follow dynamic trajectories like this, having some deceleration and acceleration, and to see how this happens a lot in congested traffic. And we want to see how the following vehicle reacts to this kind of vehicle dynamics, and we examined the following vehicles' car following behavior in response to autonomous vehicles and or human-driven vehicles, and we actually calibrated the car following models, and we found that some drivers are indeed exhibit different driving behaviors following different vehicles. And we have already uploaded the data here, and we submitted the paper that is also shared on the ResearchGate. So test 2 is about autonomous vehicle lane change in mixed traffic. This is like first of its kind in the academic research looking into both joint longitudinal and latitudinal control of an autonomous vehicle in mixed traffic where both autonomous vehicles and human-driven vehicles are present. So in this experiment setting, we see vehicle 1, 2, 4 are actually human-driven vehicles, and vehicle 3 are autonomous vehicles, and vehicle 3 wants to make a lane change to get into the gap between vehicle 2 and 4. This is very representative because in almost all lane changes on highways, a lane changing vehicle will just pay attention to these 3 vehicles around it. So we first need to look into the longitudinal control. So this time, this vehicle does not only follow the preceding vehicle 1 on the same lane, but also it needs to adjust its speed according to vehicle 2 on the target lane to sort of follow it with a certain appropriate spacing to try to merge into it. Let's see, next page. And also, in the meanwhile, the autonomous vehicle needs to pay attention to really pay attention to the fallen vehicle on the target land. When this autonomous vehicle merges into the target land, we want this vehicle 4 has enough distance gap so that there will be no rear end collision risk. Okay, and then if it is identified both front headway and rear headway are sufficient, then we're going to activate a very detailed lane change path generation and a following algorithm, going to the really detailed vehicle dynamics and sub-second or millisecond control. And we need to look into the very detailed vehicle model, considering different vehicle orientations, steering angle, that kind of thing. And so here are some field experiments. Maybe we can play some videos and let you see some screenshot. Let's say we're just to play, let's say first this, let me just turn on all of them so you can see different comparison. You see these are actually screenshots for, oh, okay, I don't see they're moving, but these are actually screenshots for 4 different sets of experiments. The first set, upper left, actually all the vehicles are actually driving a relatively steady speed. So so this actually emulates a relatively free flow traffic state. So it's relatively easy for this vehicle to for the first autonomous vehicles to make the lane changing. Let me see. For the second video on the upper right, the current lane has some slowdown, so that this mimics the congestion or shockwave from the downstream. So this vehicle, autonomous vehicle, will just follow the first vehicle and not too hectic in making the lane changing decision, just wait for a good opportunity to cut into it. Now looks like it's a good time to cut into it after the shockwave has passed. So if you look at the third video, let's say the third video, actually, yeah, the target lane has some congestion. Actually, yeah, the target lane has some kind of congestion, so it needs to wait for the target lane to adjust it to have enough distance gap, and then this autonomous vehicle is going to make the lane change. Yeah, in the fourth experiment, let's say, I don't see the vehicles, and we actually have some kind of fail-safe mechanism, just in case for some aggressive drivers that do not yield to your lane changing request. Let's say now this vehicle is ready to make the lane changing, but let's say the following vehicle, this time it successfully made it. So I think I have another video. Probably it's like in the middle of this lane changing, that third vehicle, the last vehicle, the following vehicle on the target lane will just speed up and do not yield to the autonomous vehicle here, and even that happens, so this autonomous vehicle will detect that in time and abort the lane changing operation and come back to the original lane just to avoid a rear end collision or near collision situation in response to aggressive driver. And this is very similar to our human driving behavior. Sometimes when we want to make lane changing, but the following vehicle doesn't yield to us, we have to wait for the next vehicle. So yeah, quite some interesting results. And we also actually uploaded the data online, and if you're interested, you can contact me, and we also submitted the conference paper on this. We hope to put up that conference paper manuscript online very soon. This is part of data. We compared it to the steering angle and the speed of autonomous vehicle, and we also can and human-driven vehicle. Just for your information, we also conducted a set of benchmark experiments using human-driven vehicles to do the lane change, and we see that comparing these two experiments, red curves are for autonomous vehicles and black curves are for human-driven curves, and you see for both steering angle and speed, the autonomous vehicle can do a lot better than human-driven vehicles. So, this really validates some, we sometimes autonomous, at least in some occasions, autonomous vehicles can do a lot better than human drivers. And I want to comment that there is a school of people who just want to use the learning to make autonomous vehicles drive exactly like human drivers. But I think we can make a step forward to really understand the human driving behavior and really understand the physics, and then we can take the advantages of good drivers' behaviors, but also we can overcome some disadvantages and limitations of human driving too. So that the destination of autonomous vehicle driving would, to me, not just to be driving as good as human drivers, but we want to do better. Okay, I'm going to also talk about another set of experiments. This is our really complicated control of autonomous vehicle trajectories in mixed traffic, coordinating with a signalized intersection, and I would believe this is the first of its kind. I was aware of some experiments using individual autonomous vehicles and without other vehicles, just one vehicle here. But these experiments, for the first time, actually put a fleet of vehicles, including both CAV and uncontrollable human drivers, to do the experiments. So the point of this is actually the vehicle 3, which is autonomous vehicles, will have V2I communications, and it will know the signal timing information from the infrastructure, and it will also know the downstream, so number of downstream human driver vehicles, and detect the last human driver vehicles, spacing, speed, that kind of information. And with this, the autonomous vehicle has gone through a data-driven approach to predict the following, the downstream vehicles, vehicle 1 and vehicle 2's movements, and accordingly this vehicle 3 adjusts its trajectory in response to signal timing and the downstream vehicle's trajectories to just to pass this intersection at the right time without a too big gap from the vehicle 2, for example, from the downstream vehicle, and also it doesn't have to stop. It can smoothly glide through the vehicle intersections. And next page we're going to see some interesting, okay, I'm a little bit too fast, and on this page we're going to see some experiments. So I'm going to turn on all 3 videos, see whether it's going to run. Okay, this time. Oh, so these 3 videos, we have different numbers of downstream vehicles. The first is 1 downstream human-driven vehicles. The second is 2 downstream human-driven vehicles, and the third is like 3 downstream human-driven vehicles. And you can see at the beginning, the downstream human-driven vehicles are just like us. They drive to the intersection at the really fast speed without slow down. But the result is they're gonna be blocked by the red light, and they have to make a full stop and then restart it again. So we're gonna see very soon that downstream vehicle is gonna make a stop. Let's see. Okay, so I guess they're close to making the stop. Okay, you see the downstream vehicle at least at the second figure have already made the stop. First figure made a stop. The third figure may stop. Oh, and third figure. Okay, can we turn on the video again? I see the videos disappear. Okay, all right. Ooh. Yeah, I hope let's try to get the 3 videos on, and I'll just try to explain a little more on those experiments. Yeah, okay. Maybe I can just try to turn on this video. Okay, so look. Okay, maybe just for this video, I'll just fast forward a little bit. So you can see. Okay, maybe just that we can use a 3 downstream HVs. I don't see the vehicle moving here. Okay, now the vehicle moving. You see that downstream 3 vehicles are actually driving very fast and reaching the stop line and made a full stop. Okay, then this CAV actually keeps the gap and did lots of calculation based on the vehicle to infrastructure communication, estimate the downstream street, and then once it gets here, it doesn't need to make a stop, and it just pass it right in the right time without a big gap. And this is gonna, with this kind of operation, it not only reduces a fuel for this connected autonomous vehicle CAV, but also for all the downstream vehicles. Their trajectories are also smoothed accordingly because they have to follow this smooth CAV to pass it. And also there is going to be some throughput benefit. Vehicles don't have to stop, and then there is less startup lost time, and also some safety benefit. Vehicle trajectory is smoother, the relative speed differences are smaller, that kind of thing. So it's a very interesting study and lots of benefit for transportation systems. And so okay, now we can take off the videos. And these experiments were done before actually USF had an opportunity to put together our own test bed. With the support from our university and college, we were able to put together autonomous vehicle ourselves, and we have the state-of-the-art sensors, and we have hybrid electric vehicles, we have computing and control device. We're testing and assembling this vehicle at this stage. Hopefully in a couple months this can hit the road and we can do some preliminary tests. And also, besides the vehicle, I'm also working on the communication side, and we have roadside units and onboard units. We want to make them to be like portable units. Like for portable onboard units would be like suitcase, and you can put them on any vehicles and plug them into your vehicle, with some simple plug. That's going to convert your vehicle into a connected vehicle. And portable RSUs, or like if it's hard to really connect to the signals, we can actually just do some tripod like RSUs, carry it around and set up the RSUs anywhere on the road to sort of emulate a transportation network very conveniently, flexibly, with a minimum cost. And this is going to help boost research in a number of directions, not just limited in transportation engineering, such as sensing, computing, control of connected autonomous vehicles. But as transportation engineering, we're more interested in implications to traffic and infrastructure management. There could be also some opportunities to look into cybersecurity, because this vehicle, the process of making this autonomous vehicle is hacking into a regular car and controlling all the, controlling so getting into the controllers of all these vehicle components like steering, accelerating, decelerating, this kind of thing, and flashlights, this kind of thing. There could be some, and with connected autonomous vehicles components, we can test a malicious attack and that kind of thing. So this concludes my the major technical presentation. I would like to collaborate with, acknowledge some of the collaborators and from this work, and and also some funding agencies, including NSF and USF. And so with this, I want to thank all of you, and I'll be happy to take questions if you have any.
Thank you so much, Shaw, for the great presentation. I did want to remind everybody how to use the Q&A box, which is located in the bottom right-hand corner of your screen. Simply type in any questions and or comments that you have, and we'll put them into the queue, and we'll get Dr. Lee to answer the questions. I did want to also point out that Dr. Lee did a presentation on connected autonomous vehicles in the 2018, and I added that link to the link section. That webinar was entitled Operations and Planning for Connected Autonomous Vehicles from Trajectory Control to Capacity Analysis. So that webinar is also available for our viewing. That recording is also available on our website. Shaw, we've got a couple of questions here. I will open up the evaluation as well, if you could take a few moments to complete that, as that feedback is very important. So the first question comes in and says, how do you think connected autonomous vehicle technologies will impact the highway capacity?
Yeah, this is a good question. Actually, I talked about the highway. Stephanie, I want to thank you for mentioning the previous presentation. And in the previous presentation, there was a component just focusing on the implication of highway capacity, and so that you may want to refer to so the person who raises the question could refer to that presentation, or I can send you the paper. So basically, we actually did a comprehensive literature review looking into all kinds of assumptions. I think the trend was like in 1990s that assumptions are really optimistic, like the CAV technologies gonna double or triple the roadway capacity or something like that, and other research and experiments progressed over the following decades. So most of the estimations from the academic sides are still very optimistic, and not as optimistic as before, but still it's going to increase the highway capacity by a significant percentage. But we also are aware of some field experiments and other studies that caution us about uncertainties of technology. So for example, Google Drive, the Google car was put off because it drive too slowly from too conservative. That probably would decrease the highway capacity instead. So we had a paper analyzing the different technologies and different stage of aggressiveness or the sensitivity of CAV headway settings. How would that impact the highway capacity? And recently we sort of integrated that into the cube analysis for the Tampa Bay or regional cube model. Cube is for planning, and we actually analyzed for different technology scenarios, primarily for the optimistic technology scenarios, how the CAV penetration ratios would impact the system capacity as well as VC ratio, and we presented that work to FDOT recently. If interested, I'll be happy to send you that slides. Please send me an email. So basically, overall, there is going to be lots of technology uncertainty, so we should look into different scenarios. That's what my opinion, or considering different stages of CAVs, and we should look into the field experiments and the real-world measures rather than just look into some simple car-follow models proposed by one or two researchers to evaluate the highway capacity. That's just my 2 cents.
The next question comes in and says, how would you expect to adapt to AV vehicle, or expect drivers to adapt to AV vehicles over time, or will the mix of the three types remain the same?
Oh, that's a good question. Yeah. So, I think the AV. So at the beginning, it's like AVs are going to be cautious to human drivers and vice versa. It's like human drivers will be cautious to AVs. If you see the vehicles with tons of sensors and wires sticking out from the roof, you don't want to get too close to it. Or I know some people may be curious, want to squeeze or nudge the vehicle in a way, but most of the drivers, I would assume that they don't. They have some doubts in the technologies, but as the time progresses, maybe as people are more used to autonomous drive vehicles, then this kind of panic may die down over time, and people may get to shorter headways and a little less conservative behavior in following or interacting with autonomous vehicles over time. But still, I think when we did that experiment, we want to have a follow-up experiment, is just to have a driver to follow the autonomous vehicles many times, and we want to investigate whether this driver's behavior changes as the progressive adapting to the autonomous vehicle driving. So if we do this experiments, we may be able to have some concrete numbers or concrete answers to this question.
Okay, we have another question that has come in. It says, SunTrax is about to open. Are you looking into that facility to replicate or improve your field testing?
Yes, definitely. We actually have already put together a proposal with a local company to utilize their facility. Also we talked to University of Florida I Street, and yeah, we definitely want to, and I'm also, and then from all the audience, if you're interested, I embrace all kinds of collaboration possibilities. Let's talk and see how we can utilize all the resources within Florida and within the U.S.
Okay, next question comes in. It says, would non-AV drivers be expected to test the ability of AVs to adapt? For example, speeding and weaving of non-AV drivers to get worse?
Expect to test the ability of AVs to adapt. I'm trying to understand the question. Does it mean so human drivers would does it mean the human drivers?
Yeah, there was a little clarification. It says the ability to adapt to poor driving.
Yeah, adapted to poor driving. Okay, all right, I see. Yeah, I guess it's a game. I guess it's like there is a domain of study called game theory, but it's really a sort of like a game. There is two parties, AVs versus human-driven vehicles, HVs, let's say. So if AVs are too conservative and they're going to keep a very long headway and they will yield to vehicle whenever a vehicle will make a lane changing request, then human vehicles or HVs may abuse the politeness of AVs, and that may encourage their pro-driving behavior. They're going to be more aggressive in making lane changes or speeding because they think that AVs are going to be more attentive to and defensive to their aggressive driving behaviors. So that could be a possibility, and there is some interesting simulation to see how people would take advantage of really polite and selfishless driving behavior of AVs. But as the technology evolves, maybe AVs will learn to be smart and to game with the human drivers, and then eventually maybe an equilibrium will form. And in a way, actually, in one of my study here, this study, this field experiment, this study for signalized intersection mixed traffic, if we just regulate this single AV's trajectory, it's going to force the following human driver vehicles to drive as smooth as possible, because the following vehicles cannot overpass this vehicle, and have to reproduce the same trajectory. And this is one example of using AV to improve the human driving behavior, and we can think more of these examples. Of course, if there is multiple lanes, things could be different, and we may have to have multiple vehicles to block the traffic and smooth the traffic, but that's another topic.
Perfect. Okay, Shaw, thank you so much again for the great presentation. Again, the link for his August 2018 webinar is available in the link section. I did open up the evaluation if you haven't already done so. Please take a few moments to complete the evaluation. I did want to let you know that our next Cutter Transportation webcast is scheduled for an off Thursday, and that would be May 16th, so that's in like 3 weeks or so. Again, we have Gerard Wellman and Josephine Hazelton speaking from California State University in Stanislaus. They'll be talking about transit stigma and social equity, what transportation administrators are saying about it. Again, so thank you so much for attending today's webinar, and we will see you in a few weeks. Thank you so much, and have a great rest of your day. Bye, Shaw.